So, in this lecture we will talk about the dynamic analysis of TLPs under spring and ringing waves. So far we have discussed about a TLP configuration as a geometric equivalence of a square TLP. We have been discussing about the response of compliant systems, and we started with the conceptual design, where initially the focus was weight based systems, which actually had very insignificant response to waves. We can give many examples. GBS is a very classical example of this kind of systems, where it is inertia based, topside weight was phenomenally high, but this has got some demerits like the construction cost, erection difficulties were there, erection commissioning difficulties were there. In addition to that, it also caused some soil erosion etc. So, which were discouraging for this kind of platform. Then it moved to medium water depths, where people have used semi compliant systems. Classical example was guide tower and multi-legged, multi-hinged articulated towers, but of course the deck had high responses and people have used response control mechanisms like TMD or passive dampers to control the responses. And then we moved on to the third conceptual development, deep waters, which were meant for compliant systems. The moment we say compliant systems, we had the design in two forms. So, I want to separate the whole configuration into two systems. One is rigid degrees or rigid motion, one is what we call compliant or flexible motion. So, we had 3 degrees of freedom here and 3 degrees of freedom here grouped. The classical approach was used for a tension leg platform, where the 3 degrees like heave, roll, pitch were considered to be stiff, and surge, sway and yaw were considered to be flexible. So, here the periods were from 2 to 5 seconds, here the periods were from 60 to as high as 120 seconds. So, the dominant wave period excitation force was lying in between this. So, the system was designed in such a manner that the system will not excite for the wave excitation forces, which are commonly acting in a given sea state for a deep water systems. But of course, this had very specific observations in maybe late 80s or early 90s, that these systems started showing different kinds of response in extreme waves. So, when you are subjected to extreme waves, they had shown phenomenal responses. So, people started identifying them as necessity for examining dynamic analysis of the structures for different kind of non-classical waves. So, generally if you talk about the conventional waves, may be regular, may be irregular and random, these waves does not show a specific kind of exciting forces on a given system, which can cause phenomenal impact forces on the system. Now, the moment I say impact forces, people generally understand that these forces are nothing but the forces externally caused only by vessels or ships. These are physical impacts. What I am talking about is the impact force generated by the waves itself. So, I am talking about what I call impact waves. So, waves should have a phenomenal exercise or an excitation force acting on the structure, which was observed first time in one of the practical observation platform. I will show you in the subsequent slide. So, impact waves and non-impact waves. So, the classical sea states where wave surface or wave sea surface elevation generated by ARES or PSM POSCO spectrums were not capable of simulating these kind of impact and non-impact forces on a given system. So, they were failed. On the other hand, when people started moving geometric optimization for deep water oil exploration, people wanted to know what are those extreme possibilities under which the system will fail. Okay. Though this system had shown many advantages in terms of commissioning, erection, decommissioning, cost involvement, geometric optimization, people have also said that instead of 4 leg we can go as minimum as 3 legged platforms, where triangular TLP was investigated by Nutvi et al. in 1995. Nutwich showed in 1995 the geometric optimization for the first time in ISO paper, where 3-leg platforms can also suffice in equivalency of a TLP, and then subsequently many researchers reported the advantages of these kind of systems and they studied, investigated. But of course, when complaint structures of this order come into play, people wanted to know in a clear window what will happen to the response of the systems under classical, non-classical waves, which we call as extreme waves. So identified these kind of responses, people gave a different name in the literature, they are called as springing and ringing waves. So this lecture will focus on the dynamic analysis of a complaint structure, for example a TLP, under springing and ringing waves. Now here it is very clear, the waves are categorized as springing and ringing waves. On the other hand, some literature show the response as springing and ringing responses. So here both of them are very non-classical, that is, even the response to be categorized as springing and ringing is also new. At the same time, if you really wanted to classify a wave which can cause a springing or a ringing response, even this is also new. So both of them were relatively new for the TLP observation which happened in 90s. So people enforce this kind of a new kind of response to a new kind of system, because in 80s it was then evolved as a platform concept. So people wanted to study this. Let us see how and what are the complications involved in the study and why this cannot be generated by a conventional wave model, but we have so far either using Airy's theory or Stokes fifth order or even using Pearson-Moscow spectrum. You cannot generate these kind of waves. So springing and ringing responses essentially were seen in TLPs and GVS platforms. So it was shown by the people in literature like Mercier 1982 in TLP, Hutton TLP 1980, he showed very clearly that these kind of non-classical waves or extreme waves or impact or non-impact waves can excite compliant and fixed platforms both. So they are dangerous to both kind of platforms. So that was conducted by a model test investigated on Hutton TLP model in 1980 by Mercier, and they stated that springing is caused in bending modes by second order waves. It is very important, it is exciting a specific kind of mode of vibration which is bending. We all know bending mode is more critical compared to axial linear vibration of modes, because bending induces large order deflection of member strains or stresses in a given system. When you have excitation caused at that specific mode of vibration, it is more dangerous. So springing is caused in bending modes of vibration, which is essentially caused by second order waves. So there was no necessity for higher order waves like Stokes fifth order etc. However, even in lower order waves springing responses are observed, and this was seen in both mild and severe sea states. It means even in the case of a severe or a mild sea state, for example wave height and wave periods are nominal, even then these waves are generated. Now the question is, how do you classify a given wave as a springing or a ringing wave? So that was the emerging idea in 80s or early 90s, let us say, that in a given sea state how do you actually classify a wave as a springing or a ringing wave, or how do you classify from a response a spring or ringing response, and why they are important only for compliant system, not subsequently for bottom supported structures like GBS. So that was the idea of focus in 80s and early 90s when people talked about dynamic analysis of these kind of systems under extreme waves. So ringing is of course seen in the literature as a transient response. We all know in dynamic analysis we generally neglect the transient response, we always look at the steady state response, provided the transient response considered to be dying down because of the damping present in the system. However, even in TLP or in GVS, which has got enormous damping from hydrodynamic effects, still transient response was present for a longer time duration, which was seen for the first time in a model test investigated by Mercier in 1980. Therefore that was classified as ringing. Now here you have got two kind of distinct responses. One is a transient response in bending mode, one is a steady state response in a bending mode again. So these two kinds of waves or the input wave causing this impact should be different. They cannot be, because the same wave cannot cause transient and steady state both. Okay, so there are two distinct waves now. Now interestingly you see amongst these two systems, compliant and fixed, GBS etc., you will see TLP is phenomenally designed to have the period either lower or higher from that of the excitation frequency, but on the other hand if you see, if the frequency of the wave is present in both zones like large and small than that of the natural frequency of the system, then TLP will get excited in both kinds of waves. Okay? Now that is very interesting. So TLP has seen to be phenomenally vibrant or sensitive for both kinds of waves, one is ringing wave and the springing wave. People have concluded that, saying these two responses essentially arise from what we call distinctly or extremely high steep waves. Okay. Now, conventional wave loads cannot produce these kind of steep waves. Now, the question is, how do you define the given wave as extremely high steep wave? What should be the definition for this? So, if you look at this figure which is showing the springing and ringing waves as such a schematic figure, it shows very clearly that the ringing wave has got a very phenomenal impact in terms of response, which essentially affects stiff degrees of freedom, whereas springing wave is present for a larger period. Of course, the impact is not as severe in terms of response compared to that of ringing, but present for a larger time, and that is available and causing influence on soft degrees of freedom. On the other hand, both these waves attack two distinct categorization of responses which were considered to be advantageous about 10 years back when these platforms are invented. So, now the question comes, will this platform survive these kind of waves? Now, there are two arguments here. One, what is the frequency at which such waves occur, and is it necessary that one should do analysis for such kind of waves? That is number one. Number two, when you always evolve a geometric design, maybe a TLP of a 4 leg or a geometric TLP of a 3 leg optimization, you will always look for all possible failures which arise from nature. So, that is always a principle in optimization in any geometric design optimization. So, people were looking not in terms of bothering whether what is the frequency of occurrence of these kind of waves, but people said if these kind of waves do occur, what will happen to the response of the system, because it affects or challenges both degrees of freedom, both stiff as well as flexible. Okay. Now, it is very interesting that you have a series of waves generated which affects both, which is sweeping both degrees of freedom, which was not observed and present and understood by the researchers till 90s, because people thought the input excitation frequency will be far away from the design of the TLP. That was the idea in early 90s. When we could see a wave of this order which can sweep over for a large time period, which can cover frequency of lower and higher order, people really started worrying about will TLP sustain these kind of waves. So, they gave a special name to this as springing and ringing responses, because this looks like a ringing of a bell. You can see here it is a ringing of a bell. The moment you see a ringing of a bell, it will look like that the amplitude picks up suddenly and gradually decays. So, that is why the name ringing comes from here, and this is springing because this is present for a larger period in domain, but the frequency or the intensity is not as high as a springing wave. So, one can otherwise call these waves as impact waves and these waves as non-impact waves. So, ringing waves were classified in literature as impact waves and springing waves are classified in literature as non-impact waves. Okay. To be non-technical, to be very specific and technical, the amplitude of springing waves are not comparable to that of a ringing wave, but ringing wave present for a shorter domain excites stiff degree of freedom, whereas springing wave presents for a longer domain excites compliant degree of freedom, and these two waves occur in sequence. That is the problem. So, they will have a full sweep of the entire frequency band of a compliant system like TFP, which was found to be promising for deep water exploration till early 90s. So, that was the original idea and the origin of the problem, why such studies were intuited by taking a model of an Hutton TLP. It does not mean Hutton TLP has failed in this, but people studied this as an example. So, dynamic analysis of compliant structures become more important, because this wave sweeps the entire domain of frequency of the systems. It influences both compliant and stiff degrees of freedom. Ringing of course results in fatigue failure, that was studied and shown in literature by Winterstein and Martinson in 1988 and 1992 respectively. So, they said that the ringing response which affects the stiff degree of freedom, which is caused by an impact wave, can result in fatigue failure, because it can cause pull out of tethers. Okay, that was envisaged by these researchers. Studies under these waves became important for large volume structures. We all know TLP is actually a buoyant supported system. The design by itself says buoyancy force much exceeding than the weight of the platform. So, I have to go for a large volume, because buoyancy can be achieved only by volume of submergence. So, my system is a large volume system. Therefore, studies showed in the literature that large volume structures will be affected by this. Subsequently, ringing responses are caused by asymmetric waves. You can very well clearly see here a conventional wave model will not be able to generate an asymmetric wave. Okay. So, asymmetric waves became a big problem. How they can be generated? Kim and Zhao 1995 and Jeltsin and Meyrag in 1979. As early as 80s, people envisaged that these kind of waves can cause a special kind of impact on systems. Now, Kim et al. Tried to generate these kind of waves analytically. Now let us see what are those analytical problems available in f of t, that is force generation system using a conventional wave theory. People have said that members with large length to diameter ratio, because we know that the diameter L by D ratio as far as TLP members are concerned is phenomenally different and significant. The members with large L by D will be affected by ringing responses or ringing waves, and people also said members which are inertia dominant will be also affected. So there are issues where stiff degrees and compliant degrees will be challenged by these kind of waves. So one set is affected by springing wave, one set is affected by ringing wave. So my whole platform can be challenged, okay, for when these waves are happening consequentially on a given platform. Now what do these waves cause to the structure? That is a very important question to be asked. Now most importantly, these waves cause or generate high frequency force content. Frequency will be very high, force content will be generated, whereas conventional Pearson Moscow spectrum will not be able to generate a high frequency force content from the spectrum. Okay, I will show you both the spectra. But essentially why it is? Because this is caused due to the presence of steep near vertical wavefront. For example, if I draw a wave profile physically or typical wave profile for a impact wave which is going to cause ringing, which should appear to me as a history of this sort. Let us say it should look like a bell which should converge. Now the wave will, if you look at the typical time history, this is a ringing response. If you look at the time history responsible for this kind of wave, the time history should look like a conventional silent time history which should have a sudden impact and then a conventional. So this is what we call near vertical wavefront, okay, and the amplitude of this is seen to be about 8 to 10 times higher than a conventional amplitude of Hs. So this is a very special kind of wave, and you will believe and you will know that conventional PM spectrum cannot generate this kind of waves. Okay, so that is why these waves were classified separately in the literature, saying that they are impact waves. So they have a high frequency content, and it is essentially because there is a near vertical wavefront causes. Then the response actually builds up generally. If you look at the springing response, the response gradually builds up. Generally you know the response decays. Response actually decays because of the damping effect present in the system, or the response can build up and become conventionally stable when zeta by 0.2 is available here, whereas in a springing response the response gradually builds up. For example, the response goes this way and there is a gradual build up of the response, that is called a springing response, and this is present for a larger time, then it dies down. So it is this zone which falls in the frequency of compliance degrees, like surge, sway and yaw will be challenged in this frequency content. Okay, so there is a gradual build up and gradual decay. So this was observed in springing wave. So the build up response causes worry because it is present for a larger time period, because larger time period in sense surge, sway and yaw has a time period varying from 60 to 120 seconds, so larger time period in terms of its value. And the third issue which was noticed by the researchers, where the ringing waves, the frequency of this wave is seen to be generally closer to that of natural frequency of TLP. Okay, and this is going to challenge one of the stiff degrees of TLP like heave. So it can result in unstabilized behavior of the system, because heave is controlling the TLP or the tether tension in the TLP, and if tether tension is challenged, the whole stability, static equilibrium of the platform will be challenged, because we know the equation of equilibrium depends essentially on T naught, because that is the counterpart which is balancing buoyancy force and the weight in a given system. So that will be challenged by a ringing wave, because the frequency content of this kind of wave will be as close as possible to that of a natural frequency. This was observed. Now the question is how you create a wave which will be able to cause this kind of responses. Okay? Number one, what is the spectrum available, what is the wave theory available. Number two, it has been very conventionally categorically stated by the researchers that conventional wave loads will not be able to cause this kind of responses. So it is a special kind of approach for dynamic analysis. So before we start looking at how these waves can be generated, what is the response on a given system, let us see how do we optimize the TLP geometry. As I said, in the present study what I am going to project to you, we will talk about a 3-legged TLP which is a geometric optimization of a 4-legged TLP, what we call in literature as equivalent triangular TLP, because this has shown many advantages, like it has got increased tolerance for positioning the foundation of the legs, it has got increased draft and heel tolerance. So, it becomes easy for people to commission this kind of TLP compared to that of a 4-legged TLP. They were clearly and categorically expressed by Natwij et al. In 1982. Subsequently, there are many papers referred on this which I will show you at the end of the presentation, where this statement is supported. So, we are now working at a comparison of an equivalent geometry and that of a square TLP, both, let us say rectangular and square and triangular. We will see the response on both the cases, then we will try to compare, is my optimization really advantageous in terms of this kind of response. That is the idea, because whenever you talk about conceptualization of any geometry, you must always compare the conceptualized geometry with the existing one and show the merits of the geometry compared to the older one. If it is demeritorious, we should not take it forward for any analysis or design further. So, in this study we will show the comparison between an equivalent triangular TLP with that of a square TLP, and then of course TLP is also getting affected by this in general, but triangular TLP is affected lesser compared to square TLP, as we see from the results now as we proceed further. Any questions here? So, the study which is purely on dynamic analysis based for this kind of system was a thought provoking idea in 90s, because they were special kind of waves which cannot be generated by a conventional spectra or wave theories. They have a different kinds of style of responses. They excite frequency bands of stiffer and compliant, which is sweeping away the entire phenomena of design of TLP itself. Okay, that was a catch here. Now, the question comes, what is that problem where you cannot, which stops you from not generating this, simulating these kind of waves in the analytical studies. Let us quickly see what are ringing and springing waves. Ringing and springing wave will result in excitation of transient deflection at closer frequency to the natural frequency of TLP. Springing excites motion in vertical degree of freedom, that will affect heave degree of freedom. Shape of these waves are very crucial in the analysis, because it has got to have a near vertical front for a given wave. So, shape of this wave is very crucial, and these waves should remain steep and asymmetric with respect to both the axes, horizontal and vertical, as stated by Kim et al. In 1997. Therefore, analytical wave models are not indicated in the literature which are capable of producing this kind of impact and non-impact waves. Okay. So, Kim et al. Generated these kind of waves in the laboratory, simulated them in the lab for a laboratory scale. Now, why available wave theories cannot simulate this kind of waves? When you look at the thesis stated by Sewell Sun 2006, Massachusetts, he shows that the random wave spectrum suffers serious potential difficulties. You will not be able to generate this kind of waves from a conventional spectrum, which is essentially a Pearson-Musker spectrum or a John-Swab spectrum. Okay. The shape of experimental analytical waves, if at all even created, are entirely different. You are not able to match them at all, because experimentally Kim showed these waves can be generated, analytically Sewell Sun tried to generate them and they were not comparable. Okay. So, absence of systematic method to categorize the steepness effect in the theory is a serious lacuna, because asymmetricity is not possible to create from a standard theory. So, insufficiency in these theories were higher extent, therefore, these extreme waves cannot be generated to cause impact forces on the system. That was the general conclusion given by both the set of researchers till 2006. Then what is the alternative? What do we do about it? How do we go? Use of higher order nonlinear wave kinematic theory can be applied here, but this will lead to a mathematical formulation, because they will become computationally expensive. As we all know, in a given equation of motion like TLP, where it is response dependent, the RHS and LHS of equation of motion is response dependent. If you have complexity in the nonlinear kinematic wave theory model itself, then this will impose more complication in your mathematical computations. This may even lead to non-convergence of problems also mathematically. Okay. So, you cannot use pure analytical model to develop this. So, then people said we will converge to Airy's theory, we will modify Airy's sea surface elevation with some parameters, so that I can create this kind of wave. So, Ronald Spilato subsequently for about 3-4 years attempted this and successfully came out with a model where Airy's wave theory model is modified, the sea surface elevation is modified to create a spectrum which is modified Pearson-Musker spectrum given by Mitchell in 1995. Let us see how is that wave generated. So, the current discussion is about modified PM spectrum, which is used to generate a random sea surface elevation. the P-Moscow spectrum is modified in the following format. 1. The original PM spectrum is actually a function of wind velocity, okay, whereas the modified one will be not a function of wind velocity, but a function of modal frequency. So, it is picking up a frequency wherein you want to excite a specific mode of vibration, where in my case if you want to generate an impact wave, I will pick up the mode of frequency of that of the stiff degree of freedom. If you want to create a non-impact wave, I will pick up the frequency of that of the compliant degree of freedom. So, I can always have a choice to choose what omega should I feed in my Pearson-Moscow spectrum, which is I call as modified PM spectrum as suggested by Mitchell in 1999. So, the conventional theories will not be able to generate these kind of waves, therefore, people went on to modify the given PM spectrum with a specific equation which is seen here. So, that is the modified PM spectrum, where omega m is the modal frequency, where omega is the natural frequency of the system and A eta eta is the power spectral density function, which is function of omega. Now, the wave elevation which is generated from the spectrum, because you can discretize the spectrum and get a wave elevation, the wave elevation eta of t will be given by this equation as seen in the slide now, but this is now a function of delta omega I and phi I, where omega I are discrete sampling frequencies which is picked up from the history, where n will be the number of data points in the given time history and phi I is a random phase angle. Now, you pick up the random phase angle to decide whether you want an impact wave or a non-impact wave. So, now you have a liberty to modify eta of t, which is going to be sum of wave frequencies, where you can pick up the phi value and omega I bandwidth, that is omega I minus 1 to as close as heave or as close as or as large as surge and yaw motion. So, you can pick up those frequencies and use the phi I value. So, you can generate eta of t, which will give you a different kind of wave elevation, which can be either an impact wave or a non-impact wave. For example, an impact wave should have a vertical wave front, non-impact wave is a conventional wave where it is spread for a longer period like a springing wave. So, impact waves will have a peak, instantaneous peak at a particular time t naught. This will have distinctly an higher peak compared to other kind of waves, whereas for a non-impact wave the sea surface elevation is modified. You can see the previous equation, whereas t naught is not present in the eta of t, whereas you want to generate a non-impact wave, include t naught, where t naught is the time where the impact wave is generated. So, you are creating a history which is sequential, it creates an impact wave first and then non-impact wave subsequently. Okay. So, that is the plot of the modified PM spectrum for frequency versus sea surface elevation in terms of its energy is S eta eta content, and these are impact and non-impact waves. I want you to pay attention to the wave history generated from the spectra, because you know from the spectra I can easily generate this wave, because is eta eta is an input in this generation. I take this input, apply, generate impact wave and non-impact wave. This is impact wave because there is a distinctly high wave height present in this model which is not present in this model. Okay. So, this was actually a mathematical manipulation attempted to create a special kind of wave which are called either an impact or non-impact wave in the literature, which are otherwise responsible for ringing or springing responses in a given system. Essentially, they are important for compliant systems because they sweep the entire frequency band of a compliant system, which is not present dominant in other kind of system. Therefore, springing ringing studies become more important when you have a flexible system in place compared to that of fixed systems. However, springing ringing responses were notified even in fixed platforms also, okay, but they became more interesting because the whole band of frequency now for both compliant and rigid degrees of freedom are now under challenge for this kind of waves. Okay. So, this was generated in the present study, which I will show you the results now. So, an equivalent triangular TLP which was already studied, we have derived the equation of motion for this, we know how the mass matrix and stiffness matrix come for the system, we already know all the parameters of this, and a plan which is having equivalent triangular TLP is a geometric optimization. We all know, just to recollect this, we said that the equalization can come from static equilibrium, where we know FB and W need to be balanced. We know FB is very large than W, that is a design by itself in compliant systems like this. Therefore, we said FB should be actually equal to 4 T naught plus W. So, 4 T naught is actually the 4 number stands for the 4 legged in a given TLP system. T naught is actual tension each. So I can now say either the system will have, for example, if this is square, if I say the buoyancy of the triangular system should be as same as that of the square. Why? You can ask me a question. Why? Because I do not want to have any compromise on W. I want to have the same top side detail as that of a square and triangular TLP. Therefore, once I do this statement, then I should say W plus 3 T naught. It means T naught in each leg will be much higher, that is T naught in triangular will be much higher compared to that of T naught in square, because there are 3 multiplier here. The other way is you can have the total T naught same and you can change the W. Okay. So you can have 2 equivalencies now. So what equivalency attempted in this case is tension in each leg is same, so you have to compromise on the total T naught, or tension each, the total T naught is same, tension each leg is different. So there are 2 optimization now coming up. So we have to compare this with the existing square TLP. So what are those TLPs taken for the study? So these are the existing TLPs available in the literature which are constructed and executed in Gulf of Mexico. Case 1, 2, 3, 4. I am not naming the TLP. You can easily find out the water depth is 600, 300, 600 and 1200. Now interestingly, if you compare TLP 1 and TLP 3, though the water depth may be same, okay, but the initial tension given to the system is different because of the weight. Okay. So what is the influence of a T naught on a given system? That is also seen. And if you compare, let us say case 1 or case 3 with that of case 4, you can see the water depth is practically double. Therefore, one can also see what is the influence of water depth on these kind of responses. So a category has been selected in such a manner that all parameters are inbuilt in the study itself, like influence of T naught, influence of water depth, etc. has been studied, because T naught is picked up because there is one optimization parameter available compared to that of a triangular TLP. Therefore, T naught is to be addressed. And when you look at do a free vibration test for equivalent triangular TLP with T naught per tether remaining same, one can easily find out the surge periods, heave and pitch period for all the equivalent triangular TLPs now, because that is case 1, 2, 3, 4. Here we are saying TLP 1, 2, 3, 4 with suffix. So TLP 1 is an equivalent TLP 1 is an equivalent triangular TLP with that of a square TLP of this order, provided T naught per tether remains same. So that is how it is understood. If you look at the frequency values of these kind of TLP, you will see that in all the cases mostly heave frequency is close to about 0.5 except in one case. Okay, let us address this particular issue. Remember in mind, my frequency at heave is close to 0.5 hertz. So if I see any excitation in a given system close to this value, it means I am having a resonant response in a stiff degree, which was very dangerous and not expected in a given design so far till 90s. Okay, let us see what happens when we do an analysis of this. So we all know conventional mass matrix and stiffness matrix, we need not to repeat that. Let us talk only over the damping matrix here. I am using a Rayleigh damping here, which is mass and stiffness proportional, whereas the constants A0 and A1 can be worked out from this. Now here the liberty is to pick up omega. Now in this case we have to pick up the omegas of a closer range, so surge and yaw degrees are picked up, and 5% damping was used as zeta 1 and zeta 2, so that we want to have an uniform damping in all active degrees of freedom. So we picked up those bands and found out A1 and A2, A0 and A1, applied in the mass stiffness matrix and got C, which is Rayleigh damping. Now let us talk about ringing responses caused by impact waves. If you look at this figure, I do not know whether you can intensively closely see this. For example, I will just read this figure for you qualitatively. This is response of TLP2, TLP3 and TLP4. Okay. Now TLP2 and TLP3 are compared because they have water depth of double, because TLP2 is 300, TLP3 is 600 meters, they are double, and TLP2 and TLP4 are compared because water depth is again doubled here, 600 and 1200. So influence of water depth is being seen in the specific literature. Now if you look at the frequency content of pitch, heave, pitch and surge, please carefully see here, this is my pitch response, this is my heave response, and this is my surge response in time history. When I move on to the frequency content, heave is plotted first. One can ask me a question, why it is so? Because you see here, this all depends upon how do they occur. So they occur at a frequency, this is occurring lower than this occurs closer to 0. So that is the order why this was swapped actually. Okay. Now let us look at the response in terms of time history. Look at the pitch response, this looks like a build up and gradual increase in response spread for a longer time. So, one can easily infer that this response is similar to that of a springing response. Okay. If you look at this kind of response, it has 2 frequency content, but of course this is shooting up on heave degree of freedom, which is practically equal to 0.5 because this is 1. Okay. So, the moment I see 0.5 hertz here, I remember that all platforms of TLP 1, 2, 3, 4, all of them have a natural frequency closer to this in heave degree, where my excitation energy is present at that frequency. So, I can really say that the impact wave or the ringing wave is exciting heave degree of freedom very severely, maybe in all the platforms TLP 2, 3 and 4 as well. Okay. This is about the square TLPs. Now, let us compare this quickly on the screen with that of a triangular TLP where T0 per tether is kept same. So, we look at that, the intensity of this value and the spread of this is slightly inferior compared to that of square TLP. Okay. Quantitatively we will define it later in the subsequent slides, but they are different. However, even in the case of a triangular TLP, the excitation at 0.5 hertz is seen, which was an undesirable response in heave degree of freedom, because heave is supposed to be stiff degree of freedom. Okay. Similarly, when you compare the response with total T0 same, that is another geometric equalization optimization. Here also you will notice that heave is getting excited closer, not exactly at 0.5, closer to 0.5, it is 0.6 here, closer to 0.5. However, if you look at the pitch response and surge response, they are occurring also at the heave frequency, showing very strong coupling between these degrees of freedom. So, if heave is excited, it will also cause failure in pitch motion, which is undesirable for a platform of production facilities in a given sea state. And you can easily see here they are looking like blow off of a gaseous release models. Like you can see here, the response gradually picks up and keeps on going continuously. You can see the energy content present in heave in the close frequency is spread for a broader band. The bandwidth is broader in this case. Okay. So, it means the energy content is much larger at natural frequency system. So, response is primarily triggered in pitch degree of freedom for a wide range of time period. This is similar to a bell vibrating, therefore, it is called as ringing response caused by impact force. This is noticed in both the geometries of TLP, both rectangular, I mean square and triangular. If you compare the ringing response of pitch degree of freedom of TLP 1 and 3, because 1 and 3 have the same water depth 600 meters. However, at the same water depth with different tether tension, it is seen that increased tension enhances pitch response, which is the other way generally. Okay. When you have increased tension, people think that the platform will be more stable, response will be lesser, but it is vice versa here when you are subjecting it to an impact wave, which is true for both the geometries. Pitch response in triangular TLPs are found to be slightly lesser compared to the square ones. If you further compare the pitch response of 2 and 3 and 4, 2 is at 300 meters, 3 is at 600 meters, 4 is at 1200 meters, where I said there also there is an increase of 50% response between say 300 and 600 meter. It is further increasing by another 50% from 600 to 1200 meter. It means water depth plays a very significant role in these kind of responses in both the geometries, triangular as well as square. It is very interesting that the increase in water depth does not enhance the ringing response significantly in terms of the content in triangular TLP compared to the of square TLP for a specific case where T0 per tether is kept same. Okay. So, in ringing response in triangular TLP under impact forces are generally seen to be lesser than that of a square. So, if you attribute pitch response to one of the impact waves as ringing responses as ringing phenomena, which is undesirable. However, triangular geometry shows lesser response compared to square geometry. Therefore, this can be a futuristic design for TLP in deep waters. Okay. That is the conclusion what we have for impact waves. Let us see what happens in non-impact waves. Non-impact wave is a generic wave which is present for a larger period but a comparable wave height. Let us see what happens in that case. Again we are comparing square with that of equivalent triangular where T0 per tether is kept same, and these are non-impact waves in both the cases. So, I am having TLP 2, 3 and 4, 300 meter, 600 meter, 1200 meter water depths. You will see that again the bandwidth in terms of greater water depths is larger further in heave degree of freedom, which is also not acceptable. Okay, because the energy concentration is higher for square TLPs, whereas when you look at the triangular TLP, the bandwidths are minimum or lesser compared to that of square, shows that the energy content present in the specific frequency which is causing a non-impact response or a springing response is lesser of order compared to a square geometry, though it is excited there also, but there is a content present in a lower order. That is true in the case of other equalization of triangular TLP also. So, this tells me a simple conclusion that heave response is triggered at frequency nearer to the natural frequency springing response. Broadband indicates energy content is larger present in both the geometries. By comparing springing response of TLP 1 and 3, TLP 1 is at 600 meters and TLP 3 is also at 600 meter, same water depth but different tether tension. Heave response and non-impact wave decreases with increase in tether tension, which is generally vice versa in theories. Heave response of triangular TLP seems to be lower or lesser compared to that of square ones, and there is always a significant increase of response compared to the water depth, which is seen in both the geometries. Heave response in all square TLP shows a burst off, which indicates that there is no rapid buildup. However, there is a rapid buildup available in equivalent triangular TLPs, which is associated in literature as a beat phenomenon. This is what people call as a beat phenomenon. So, this type of response makes square TLP more prone to fatigue failure because it is happening in heave degree of freedom. The repeated response buildup will cause decay of tether forces, and that will result in fatigue failure of tethers. And you can say the response caused by non-impact wave in heave degree of freedom is a near resonating case, which is alarming. So far this kind of response was not explicitly told and expressed in literature till researches of this order were conducted and carried out. So, the results are very simple in this case. Impact waves cause ringing response in pitch degree, increased tether tension enhances pitch response in both geometries, increased water depth enhances pitch response due to impact waves, but of course this is lesser in triangular TLP compared to the square one. Pitch response in triangular TLP under impact waves are much reduced compared to that of a triangular square TLP in both the geometry. Broadband response is seen in frequency response in heave degree of freedom, which is caused by a non-impact wave, which is called springing response. Heave response on a non-impact wave decreases with increase in tether tension, and heave response indicates a beating phenomena in heave degree of freedom for square TLP under non-impact waves, which is of course not seen in triangular TLP. Of course, the study has got lot of references. Pilato 3 references, Kim et al 2 references, Kelgen, Murong, we have been used wave structure interaction, wave current interaction deporters in 1979. Winterstein nonlinear vibrations for extreme waves in fatigue, Martinson and Winterstein and Uday, fatigue in TLP due to second order springing responses. Michel we was given a C spectrum modification for Pearson-Musker spectrum in 1999. Of course, the results what we presented as a support from the following publications of my own: 2010 ringing response, 2011 springing ringing response international building progress, 2013 dynamic response under extreme waves, Genem, myself and Bhattacharya in a book on analysis and design with feed Changhua University, then springing response steady state transient response of TLP under wave loads, European Congress Southampton, and myself and Jain ringing response in IIT Madras INSHO 2009. We can also look at the response of extreme waves. I will quickly take about 5 minutes to explain what are extreme waves. Extreme waves are very interesting. The causes for occurrence are very simple. They have a nonlinear wave-wave interaction. Wave current interaction creates extreme waves. Bathymetry, wind effect and directional effects are responsible for this kind of waves. Space and time focused waves are actually extreme waves. They are seen to be occurred in Dropner platform January 1, 1995, recorded what they call as a New Year wave because it has been recorded on 1st January 1995. So, it is called as a New Year wave. The location was North Sea about 100 miles, and it has been also seen in Yura Harbor in Japanese Sea. They look like this as a New Year wave or Dropner wave. They also have a distinctly high wave front, which is 20 closer to compared to 5. So, it is about 4 to 5 times near vertical wave front. So, this was also an impact wave seen as a Dropner or a New Year wave. They have different effects on structures. They cause irreparable damages to ships and offshore structures. They create inoperable conditions and discomfort to crew on board. The knowledge of these waves are very important to analyze them for extreme behavior. Study was done again on TLP, literature review are given here. Freak wave model was generated using a John-Square spectrum. In this case, earlier case was modified PM spectrum, and you can see here the random wave measured and the random wave. I will show you the comparison quickly here. Okay. This must be somewhere here. Yeah. This is a recorded New Year wave, the simulated New Year wave. The recorded North Sea extreme wave, this is simulated extreme wave. If you look at the time for which the period has been done, Hs, Hmax and the ratio. If you look at the simulated wave, they practically have the same ratio and they practically have a closer Hs from simulation. Similarly, if you look at the extreme wave, Hs, Hmax and ratio, simulated wave has a closer Hs, closer Hmax and the ratio is practically closer. So, how they have been simulated is using this relationship. So, in a random wave we pick up 80% of randomness from the sea surface elevation, 20% of transient wave from the sea surface elevation and combine them and create a wave. Okay. Once you create this wave, the simulated wave has got a very close match of the real observed wave in the sea front taken by the literature. Then of course, we have the mass matrix, stiffness matrix, damping matrix for TLP, hydrodynamic forces using Morrison equation. The solution is done using Newmark's beta method in time domain, which I will discuss slightly later, but however the solution procedure is given here. The solution domain is also explained here, the results are here. Then we have applied for a 4-legged TLP and the results are like this, which you see again here. In case of heave, it is getting excited closer to the natural frequency of the system. There is a second peak occurring closer to the natural frequency of that of the pitch, which shows a strong coupling between these 2 degrees of freedom, which was again seen in extreme waves also. So, the results conclude that extreme wave can excite TLP near to its natural frequency in heave and pitch degrees of freedom. TLP is also seen to be sensitive to wave directionality effects. The realistic extreme waves can be simulated using a freak wave model as suggested by the researcher now. Increase in water depth increase the response by 50% and subsequently by 80%. So, this lecture covers dynamic response analysis of a combined system like TLP, starting from the history why TLP was selected for this particular problem of an origin and how the waves can be generated, why these waves cannot be generated using a conventional wave theory models and PM spectra or John-Square spectra, what modification you have got to do for this, where the reference have been taken, how the published results have been validated and how extreme waves show very alarming response on a combined system like TLP, which is very important for design conceptualization for ultra deep waters if you want to really use TLP as a system for deeper water depths in future. Any questions here? We close here.